It is not appropriate to run 1500 feet between two transformers with only two wires without a grounding conductor. The National Electrical Code, or NEC, requires a grounding conductor for all electrical circuits. This grounding conductor serves several important purposes, including firstly, safety. The grounding conductor provides a path for fault currents to flow back to the source, reducing the risk of shock or fire. Secondly, equipment protection. The grounding conductor helps to protect equipment from damage caused by voltage surges or other electrical disturbances. Thirdly, noise reduction. The grounding conductor helps to reduce electrical noise and interference by providing a low resistance path for current to flow. In the case of the proposed installation, the long distance between the transformers creates a significant potential for voltage drop and noise. Without a grounding conductor, the current returning to the source will flow through the equipment, causing voltage drops and electrical noise. This can lead to equipment damage and malfunctions. Additionally, without a grounding conductor, there is no path for fault currents to flow back to the source. This increases the risk of shock or fire if a fault occurs. Therefore, it is essential to run a grounding conductor between the two transformers to ensure safety and proper operation of the electrical system. When dealing with electrical installations, particularly those involving transformers and long distances, it's crucial to understand the role of grounding and bonding. Grounding and bonding are two distinct but interconnected concepts that are essential for ensuring electrical safety and preventing equipment damage. Firstly, let's define grounding. Grounding refers to the intentional connection of electrical circuits and equipment to the earth. This connection provides a low impedance path for fault currents to flow back to the source, which in turn helps to trip circuit breakers or fuses and to energize the circuit in the event of a fault. Grounding also helps to stabilize voltage levels and reduce electrical noise. Secondly, bonding. Bonding, on the other hand, refers to the connection of non-current carrying metallic parts of an electrical system to create an electrically conductive path. This includes things like metal enclosures, conduits, and equipment frames. Bonding ensures that all of these metallic parts are at the same electrical potential, which minimizes the risk of electric shock if someone comes into contact with a faulty piece of equipment. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding in Article 250. These requirements are designed to ensure that electrical systems are installed and maintained in a safe and reliable manner. Some of the key requirements for grounding and bonding include the use of a grounding electrode system, which typically consists of ground rods, ground plates, or metal water pipes that are buried in the earth. The grounding electrode system must be connected to the electrical system using a grounding electrode conductor, which is typically made of copper or aluminum. The NEC also requires that all non-current carrying metallic parts of an electrical system be bonded together using bonding jumpers or other approved methods. This includes bonding the metal enclosures of electrical equipment, as well as bonding the metal conduits and raceways that carry electrical conductors. In the specific scenario of running 1500 feet between two transformers, the need for a grounding conductor is even more critical. The long distance between the transformers can result in significant voltage drop and impedance, which can make it more difficult for fault currents to flow back to the source. Without a grounding conductor, the fault current may have to travel through the earth or other unintended paths, which can increase the risk of electric shock or fire. Therefore, the NEC requires that a grounding conductor be run along with the phase conductors between the two transformers. This grounding conductor provides a dedicated low impedance path for fault currents, which helps to ensure that the circuit breaker or fuse will trip quickly in the event of a fault. In addition to the grounding conductor, it is also important to ensure that the metal enclosures of the transformers are properly bonded together. This will help to minimize the risk of electric shock if someone comes into contact with a faulty transformer. To further elaborate on the importance of a grounding conductor, consider the following points. Firstly, voltage drop. Over long distances, conductors exhibit impedance, which causes voltage drop. This voltage drop can affect the performance of equipment connected at the end of the run. A grounding conductor helps to stabilize the voltage by providing a return path for current. Secondly, impedance. Impedance in the circuit can also lead to voltage imbalances, especially in three-phase systems. A grounding conductor helps to balance the voltage by providing a low impedance path for current to flow. Thirdly, harmonics. Nonlinear loads can introduce harmonics into the electrical system. These harmonics can cause overheating and other problems. A grounding conductor helps to mitigate the effects of harmonics by providing a path for harmonic currents to flow. Fourthly, transient voltages. Lightning strikes and switching surges can introduce transient voltages into the electrical system. These transient voltages can damage equipment. A grounding conductor helps to protect equipment from transient voltages by providing a path for the voltage to dissipate. Fifthly, electrostatic discharge. Electrostatic discharge, or ESD, can damage sensitive electronic equipment. A grounding conductor helps to prevent ESD by providing a path for static electricity to discharge safely. Sixthly, electromagnetic interference. Electromagnetic interference, or EMI, can disrupt the operation of electronic equipment. A grounding conductor helps to reduce EMI by providing a shield against electromagnetic radiation. Seventhly, personnel safety. Perhaps the most important reason for a grounding conductor is to protect personnel from electric shock. In the event of a fault, a grounding conductor provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and energizing the circuit. In the absence of a grounding conductor, the fault current may flow through a person who comes into contact with faulty equipment, resulting in serious injury or death. When selecting a grounding conductor, it is important to choose a conductor that is sized appropriately for the circuit. The NEC provides tables that specify the minimum size of the grounding conductor based on the size of the phase conductors. It is also important to ensure that the grounding conductor is properly installed and connected. The NEC provides detailed requirements for the installation and connection of grounding conductors. In addition to the grounding conductor, it is also important to ensure that the metal enclosures of electrical equipment are properly bonded together. Bonding ensures that all metal parts are at the same electrical potential, which minimizes the risk of electric shock. The NEC provides detailed requirements for bonding metal enclosures. When working with electrical systems, it is always important to follow safe work practices. This includes wearing appropriate personal protective equipment, or PPE, such as gloves and eye protection. It also includes energizing the circuit before working on it. If you are not qualified to work on electrical systems, it is important to hire a qualified electrician. In summary, a grounding conductor is an essential component of an electrical system. It provides a path for fault current to flow back to the source, reducing the risk of shock or fire. It also helps to protect equipment from damage caused by voltage surges or other electrical disturbances. The NEC requires a grounding conductor for all electrical circuits. Therefore, it is essential to run a grounding conductor between the two transformers to ensure safety and proper operation of the electrical system. Understanding the National Electrical Code is crucial for safe and compliant electrical installations. The NEC, updated every 3 years, provides comprehensive guidelines for electrical wiring, overcurrent protection, grounding, and equipment installation. Article 250 specifically addresses grounding and bonding requirements, emphasizing the importance of creating a low impedance path for fault currents. This path ensures that protective devices, such as circuit breakers and fuses, operate quickly to clear faults, minimizing the risk of electrical shock and fire. The NEC also outlines specific requirements for grounding electrode systems, which include ground rods, crown plates, and underground metal water pipes. These systems provide a connection to the earth, stabilizing voltage and providing a reference point for electrical systems. The size and type of grounding conductors are also specified in the NEC, based on the size of the ungrounded conductors in the circuit. Proper bonding of metallic enclosures and equipment is another critical aspect of NEC compliance. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of shock if a fault occurs. The NEC provides detailed instructions on how to bond metallic enclosures, raceways, and equipment using bonding jumpers and other approved methods. In the context of the described scenario involving a 1500-foot run between two transformers, the NEC requirements for grounding and bonding are particularly relevant. The long distance increases the potential for voltage drop and impedance, making a dedicated grounding conductor even more essential. Without a grounding conductor, fault currents may have to travel through unintended paths such as the earth, which can be less effective and increase the risk of shock. The NEC also addresses the use of separately derived systems, which is relevant when using transformers to step up or step down voltage. A separately derived system is an electrical system whose power is derived from a source other than a service. Transformers are commonly used to create separately derived systems. The NEC requires that separately derived systems be grounded and bonded in accordance with specific rules, which are designed to ensure that these systems are as safe as service-supplied systems. In addition to the technical requirements, the NEC also emphasizes the importance of qualified personnel. Electrical work should only be performed by licensed electricians or qualified individuals who have received proper training. This is because electrical work can be dangerous if not performed correctly. The NEC provides a wealth of information and guidance on electrical safety, but it is important to consult with a qualified electrician or electrical engineer to ensure that your electrical system is compliant with the code. Understanding the NEC is an ongoing process, as the code is updated every 3 years to reflect changes in technology and industry best practices. Staying up to date with the latest edition of the NEC is essential for anyone involved in electrical work. In summary, the NEC is a comprehensive set of guidelines for electrical safety and compliance. It provides detailed requirements for grounding, bonding, overcurrent protection, and equipment installation. By following the NEC, you can help to ensure that your electrical system is safe and reliable. Always consult with a qualified electrician or electrical engineer to ensure that your electrical system is compliant with the code. Remember that electrical safety is a shared responsibility, and everyone should be aware of the risks associated with electricity. To delve deeper into the practical implications of grounding and bonding in the context of the provided scenario, let's consider a few additional factors. Firstly, the type of soil in which the grounding electrodes are installed can significantly affect the effectiveness of the grounding system. Soil resistivity varies depending on factors such as moisture content, temperature, and chemical composition. High soil resistivity can impede the flow of fault currents, reducing the effectiveness of the grounding system. In areas with high soil resistivity, it may be necessary to install multiple grounding electrodes or use ground-enhancing materials to improve the conductivity of the soil. Secondly, the presence of underground utilities can also affect the design and installation of the grounding system. Underground pipes, cables, and other metallic structures can provide unintended paths for fault currents, potentially creating hazards. It is important to locate and identify all underground utilities before installing grounding electrodes. Thirdly, the type of equipment being powered by the transformers can also influence the grounding requirements. Sensitive electronic equipment, such as computers and control systems, may require more robust grounding to prevent noise and interference. In these cases, it may be necessary to use isolated grounding systems or other specialized grounding techniques. Fourthly, the presence of lightning can also pose a significant threat to electrical systems, particularly in areas that are prone to thunderstorms. Lightning strikes can induce high voltage surges that can damage equipment and cause fires. A properly designed grounding system can help to protect against lightning strikes by providing a path for the surge current to flow to ground. The NEC provides specific requirements for lightning protection systems, which should be followed in areas with a high risk of lightning. Fifthly, regular inspection and maintenance of the grounding system is essential to ensure its continued effectiveness. Grounding electrodes and conductors can corrode over time, reducing their conductivity. It is important to periodically inspect the grounding system and replace any damaged or corroded components. Sixthly, proper documentation of the grounding system is also important. This includes maintaining records of the grounding electrode locations, conductor sizes, and test results. This documentation can be helpful for troubleshooting problems and for verifying compliance with the NEC. In addition to the technical aspects of grounding and bonding, it is also important to consider the human factors. Electrical safety training should be provided to all personnel who work with or around electrical equipment. This training should cover the hazards of electricity, safe work practices, and the proper use of personal protective equipment. Employees should also be encouraged to report any electrical hazards or concerns to their supervisors. In conclusion, grounding and bonding are essential for electrical safety and equipment protection. The NEC provides detailed requirements for grounding and bonding, which should be followed in all electrical installations. By understanding the principles of grounding and bonding and following safe work practices, you can help to prevent electrical shocks, fires, and equipment damage. Always consult with a qualified electrician or electrical engineer to ensure that your electrical system is compliant with the code. Remember that electrical safety is a shared responsibility, and everyone should be aware of the risks associated with electricity.